Hello, this is my presentation for CS50 for the project WRAC, a population simulator, WRAC meaning weighted relative abundance criterion. My name is Aris Padotis. You can find my GitHub links and my edX links right here. You can see them on screen currently. I'm in Athens, Greece, and I'm doing this as of February 5th, 2026. Let's take a look at some of the visualizations that come out of the population simulator at hand over here. It's called weighted relative abundance criterion because of the theoretical framework that is being used. Now, we have a bunch of different key features of the visualizations, like the sum of the shares, which has to do with summing the fair share of every resource for a specific subset of individuals. The population growth chart over here, which is essentially the population that grows up to 40,000, as you can see, individuals at some point in the simulation. We have the rates of different things, and you'll see that blue is the birth rate, orange is the death rate, and green is the growth rate. So that's what everything on this image is. You can see that the growth rate is, of course, a little bit less than the birth rate just because we have a negative death rate, right? Then we have raw stats, which would be not the rates, but the exact amounts of things. And you can see they have the same color coding as before. Now, this is the population pyramid, and this is a quite healthy visualization of it. You'll see this key visualization in many different population dynamic simulations. The productivity, how much every individual is producing, and this can be negative because if somebody's consuming more than they're producing, it can be negative. The raw resources, notice the axis over here. You'll notice that it doesn't actually change too much because the axis is so wide, we never reach the maximum capacity the blue line would represent. The weights themselves would be the modification of the fair share of an individual. I'm only listing the first 100 individuals here so that we can see some sort of variation here. And then we have the consumption, and it follows pretty much the same trends as before. Some people are consuming a lot more than their fair share. Now let's look at the distributions of things in a little bit more of a 3D setting. We've got two resources. That's why you see two big blue distributions per each one of these resources. And it's a specific exponential function that I've put up here. I think it might actually be 1 over x now that I'm looking at it. Of course, the weights again redistributed in much the same way. Now we're going to look at the actual command that I used in order to run this. You'll note that this is actually quite resource heavy on your computer. You'll notice that the first thing that's going to pop up is the initialization, and there's 3 resources now instead of 2 that were before. It's a little bit laggy. Now we're going to run the simulation. You'll notice that it goes really quickly at the start, but it starts slowing down. Now, if you do not like the fact that it's so resource intensive, you could at every point just Control-C, Control-E, or whatever, just stop the execution of the program, and it would actually use whatever cycle number you're on. It would normalize everything in order for you to view the specific window that you did. It's not as if it would discard your run. That pretty much wraps it up for my population simulator. You'll notice that here in the image that we've got at the end, we see more resources because I actually used the command that puts 3 different resources instead of 2 that we were tracking previously when I looked at the image, the static image that I had in my folder. You're free to play around with this. This is my submission for CS50.